So welcome everybody, and I would like to welcome our lecturer for this lesson. It's Michael Wong from the University of Sydney, and he will talk about optimization of a non-invasive biomonitor for exploration class human spaceflight. So Michael, would you start your lecture?
Hi, good morning, good evening, and good afternoon, everyone. Greetings from Sydney, and thank you very much for joining this session. I'm just going to share a screen now, and I'll just get Sabina just to confirm that that does come up. Can you see that, Sabina?
You are... Yes. Now we can see it, yeah, perfect.
Great, and so thank you very much for everyone for having me today. Today I'm going to give a brief overview of some of the work that we've been doing at the University of Sydney in our review of what have been historical and then current terrestrial and then spaceflight applications for biomonitoring, in the hope that that might be able to provide some sort of contribution towards the work that's been done in baselining what would be needed for exploration class human spaceflight in terms of keeping people healthy, wealthy and wise on a exploration class spaceflight to Mars or elsewhere. Just a special thanks to Dr. Xiaofeng Wu and Professor Alistair McEwen at the University of Sydney Biomedical Engineering and Space Engineering departments, as well as a long list of students and lecturers that have also contributed to the work, as well as Professor Sued Rudkovi at the Harvard Medical School, who we've been collaborating as well. Also, special thanks to so many of you who've reached out over the last few hours just with interest around this project as well. Today I will present some of the work that we've been doing, but hope that this will be part of a longer term discussion amongst many of you together with us, and great to see that there's so many people excited about something we're quite passionate about here at the University of Sydney. And with some collaborations to date. As you know, in the last 3 years here in Australia, the Australian government has launched an Australian Space Agency with key goals in partnering with other collaborative institutions, including NASA and other around the world, in developing both spaceflight technology, but also around garnering interest and research interest in the field. Also, special thanks to colleagues at Harvard Medical School, the Cerebral Palsy Alliance, Remarkable, and the Westmead Clinical Schools, which I'm part of as well. So some of the inspiration that has driven a lot of this work has spent a bit of the time that I've spent in a previous capacity. I've moved here to the University of Sydney from a long career with the World Health Organization, and most recently worked in remote settings in the Solomon Islands. And as some of you already know, the Solomon Islands is a group of over 900 different islands in the Indo-Pacific region. Some of them are in very remote settings. And so my work in terms of working with remote access to healthcare, as well as health information systems, is that you had the problem when you're going out to an island to work with communities to distribute vaccines or to deliver health commodities, including life-saving and essential medicines. Some of these communities are outside of the grid in terms of not only power grids, but also around mobile phone reception, and very, very difficult to access, like many other remote settings that you may be familiar. Some of these settings in the Solomon Islands, for example, if there was a medical emergency on an island, it would take maybe 6 to 9 hours by boat as the most effective way of getting to the nearest health clinic where you could get medical attention for something like an acute emergency, like the need for an appendectomy, or if you had required urgent surgery or medical care. You can see the parallel that we are drawing here, in that a remote setting like the Solomon Islands is not unlike other settings that you'd have in terms of your system architecture for a long-term exploration class spaceflight. And so you can see that this has driven some of the interest that builds upon the current unprecedented level of interest around human spaceflight to Mars, notwithstanding the work that we've seen today amongst the exciting presentations here at the Mars Society convention, and that spaceflight and human spaceflight to Mars, and in terms of the exploration and eventual settlement of that planet, has a lot of significant implications in terms of how we want to have humans move there and what would happen if problems happened along the way. One of the long-term objectives of NASA's human spaceflight activities has been around creating a healthy environment, as outlaid in the very, very large NASA Human Research Roadmap. But there has also been increasing interest from other agencies, including the Australian Space Agency, not to mention private sector, as well as research institutions like us at the University of Sydney, and many of you who are participating today. And so we wanted to figure out what would be the feasibility of implementing some sort of real-time monitoring system, whether that be something that is inserted into a human, i.e. an invasive device, or something that's wearable, like many of the technologies we see today, and how could we simulate that within an exploration class human spaceflight. And in order to address that question, which is the big question of my research, we had to answer a lot of smaller questions first. And so the first one that I'll discuss today and would like to open up to discussion is what new biomonitoring knowledge is needed and what new technologies or development might be required in either to support current standards or modify standards for future exploration class human spaceflight. I use the word exploration class in terms of a long trip rather than something that's low Earth orbit for the rest of the presentation. So when we conducted our literature review, we reviewed historical terrestrial biomonitoring devices. As you will know, there has been a lot of interest in the idea of adapting or spin-offing terrestrial biomonitoring devices that look at keeping people monitored on an Earth setting. And the spin-off of those devices for human spaceflight purposes have attracted a lot of attention, but less systematic research. Building on that, we also looked at a literature review of historical human spaceflight biomonitoring devices, going all the way back to the Vostok program. And when we combined the two, we started looking at what were the high-level system features of those systems, both in a terrestrial but also human spaceflight setting, both historical, and then created a summary of what would be the concept gaps, what would be the bare minimum needed for system development in terms of what wasn't being done for a biomonitoring device for human spaceflight. And based on that, we created a generic human spaceflight biomonitoring system architecture that we're very keen to keep on working with, both internally here within our collaborators, but also open for other ideas as well within the group. And finally, in terms of a paper that we'll be releasing shortly, it will be we've suggested some areas for future research adaptation, something that we'll discuss at the end of these slides as well. As you all know, there are a multitude of conditions that could happen to a human on the way to Mars. In terms of low Earth orbit and also exploration class spaceflight, i.e. we're not talking about what necessarily happens when humans do get to Mars, but what would be the conditions that would need to be either treated, mitigated, monitored on the way there. And as you can see here in the left-hand column, there are a list of conditions that are currently monitored by monitors either in space flight or in a terrestrial setting. And on the right-hand side, we had created a small index of what would be the likelihood of incidence of that event happening. For example, human dosimetry in terms of monitoring radiation exposure, of course, is both anticipated and common, whilst having a myocardial infarct on the way to Mars is probably less common, but could potentially be life-threatening. This provides a backdrop for some of the considerations we've made and also others have made historically, and that we've brought into our review. As you will be familiar with some of the developments that have happened on Earth, since the 1950s, we have seen a transition from using manual reagents, things like urinalysis, strips for urine analysis, as well as specific reagents for things like blood glucose measuring, to more automated systems that then use the system architecture for developing using the readings from these manual reagents and then triggering what we see now as automated medical delivery systems. The case in point being things like the implantable cardiac defibrillators that use waveforms, i.e. arrhythmias within a heart that then trigger a response that could then automatically deliver some sort of life-saving cascade within the system. Another one would be blood glucose in an automated system where you have there in the someone's belly button is exposed. I hope that's fine for this mass convention. But you could have a blood glucose machine that automatically takes up blood glucose readings, and if it is high or low, it will trigger a delivery system of insulin or other drugs. And so the key system concepts we've seen both in a terrestrial sense, but also more recently in things like military applications around that, it is really important to reduce latency of how long it takes for a reading to then get to either a clinician, someone treating, or someone monitoring, or even a system, in order of reducing time needed to make clinical decisions, i.e. Delivery of life-saving drugs or interventions. Second has been the interest in using actively actuated biomonitoring, or as another word we use for feedback systems, i.e. Can what you read trigger something that could help you in terms of a system architecture that's electronic. And then lastly, we have seen an increasing push towards integrated multiple analytes such as respiration, pulse oximetry, and heart rates. Things we've seen not only in military applications in terms of wearable technologies, but also more recently, as some have seen in presentations earlier in this convention around things like hexaskin and things that are being used in the International Space Station. So in terms of that segue, in terms of human spaceflight biomonitoring, and hexaskin being one of them, there have been leaps and bounds in terms of since the original Vostok missions, Mercury and Gemini, and in terms of developing human spaceflight monitoring systems. And we like to joke, the developments have reached as far from invasive rectal probes on early missions in the Gemini era to more telemetric compression garments that we see now with the Canadian Space Agency in terms of hexaskin. Some of the key concepts that we have seen in terms of this evolution of biomonitoring systems for human spaceflight since the 1950s has been a transition towards, away from non-invasive systems. We now, instead of using things like temperature probes that are inserted into an astronaut's personal space, have been transitioned into more non-invasive measures, including wearable technologies, but also other interventions such as ultrasound on the International Space Station. The use of telemetry and transmission of data at this stage, both in terms of the hexaskin and other wearable technologies, are a docking technology, i.e. Latency will be an issue. There isn't much latency issues when you're going up to the space station because it's not comparatively far in terms of when compared to a space flight to Mars, where you've got some delay in terms of your mission and base on Earth, presumably. But then lastly, we are starting to see some discussion around integration with environmental control and life support systems, biomonitoring systems, something that was initially discussed many years ago in the Skylab, but now more recently, as you will have seen, in limited detailed discussion with the SpaceX and Dragon suits. At this stage, we have seen very little, if not no, actively attenuated systems, i.e. automated medical delivery systems, another area very ripe for research. And so the aim here is some of you will be familiar with that scene in the movie, the James Cameron Aliens movie, where the Marines are sent down to a seemingly quiet planet, and they have their wearable technologies that give various PPG, ECG, and it looks like EEG readings of how they are doing in terms of how safe would it be being launched into a hive full of aliens that were hungry for them. And so that didn't turn out well, and we want to avoid not only what seems to be what was a disastrous situation for those Marines, but also perhaps maybe a very, very primitive way of looking at what wearable technologies will be in the future, i.e. Some of the relevant system concept gaps that we are seeing at the moment is that gap in terms of feedback systems. It's great to know, for example, that that the person being monitored might have something wrong with them, i.e. arrhythmias detected on an ECG, or even certain annihilates going out of the normal areas or measurements, but it is another thing to be able to have an automated system that could deliver something bearing in mind the distance issue, which is one of them, that will feature on a long exploration class spaceflight mission. Secondly is around that idea of telemetry, both in terms of quality, i.e. are your measurements accurate enough within the systems that we've seen so far around things like pulse oximetry, ECGs and EEGs, but more importantly, how latent are those signals? Are we getting a signal of someone's arrhythmia up to 9 or 13 minutes later than it's actually happened? Because that system would then not be effective in terms of the point around delivering point of care feedback systems such as cardiac shocks and automated medical delivery. And then lastly, this larger kind of issue around integration with environmental control and life support systems. As you'll be familiar, in the 1970s around Skylab, the discussion was that you had some sort of carbon dioxide monitor within a spacesuit that was then linked up to an umbilical cord that went back to the environmental control and life support ECLS system on board, something that we have not seen a lot of published research, if any, at this stage in terms of human spaceflight. Based on those gaps, you'll see that we currently work with what we've proposed as a human spaceflight biomonitoring system architecture, i.e. drawing various physiological signals within what we use as an area network, thinking of the human body as some sort of area network that has various electrical signals, and how those signals could then be logged within either a remote or portable unit within either a spacesuit or within the actual environment, that could both amplify and filter those signals in a way that's processed and then stored, but also communicated to either real-time monitoring devices, something that could give you either a remote interface that you were using or something offline that could feed back into another feedback loop, as you can see in this bottom corner here, around automated system delivery systems. All, of course, with the large caveat that there have been significant discussion around what those kind of data logging systems will use in light of other technological advancements, including the big one, transition from HF radio and TDRS and Bluetooth to what will happen if things like Starlink continue to happen, and what implications that will have for how far Starlink would reach, i.e. beyond low Earth orbit into something that you could potentially transmit and help with signals in exploration class spaceflight. Again, and the third time I'm saying it, but it is a significant issue, is around how do we feel that this is integrated within environmental control and life support system networks. We tend to think of ECLS as using environmental readings like oxygen and carbon dioxide, and it's important as us as carbon-based organisms to think about that, but also thinking about long-term issues that could be drawn from that physiological area network, things like blood analytes and other electrical readings. So here at the University of Sydney, we continue to look at developing and working with existing telemetry systems, including satellite, in collaboration with colleagues at CSIRO, our science agency, as well as the Australian Space Agency and other academic institutions, as well as some private institutions that have expressed interest in terms of how can satellite technology can be used for remote patient monitoring, and do they have, again, these do they have a standalone monitoring system, or do they have a feedback system like an automated medical delivery system, or maybe a combination of both? Something that takes up a bit of our time here at the School of Aerospace, and as well as biomedical engineering. Secondly, we're particularly interested in ongoing work in how that can be integrated with spacecraft environmental control and life support systems, and that can vary from spacecraft to spacecraft. Very, very exciting to see the work that's been happening, not only recently with the ISS, but also around the Dragon work at SpaceX. And then lastly, and maybe a small elephant in the room, this idea around cybersecurity. If you had a automated medical delivery device that was attached to a human or a crew member on a flight to Mars, that is an electrical signal that poses cybersecurity issues in terms of if you were able to hack that signal, that would have significant medical outcome implications, as well as, not to mention, there's an emerging field that have been discussed not only at this Mars Society convention, but also previous ones around the ethics around computer autonomy of medical point of care. So thanks again for joining the session. I'm happy to take any comments and questions for the duration of the session, but just thanks again for joining and for your interest in how we can improve biomedical monitoring and potentially even treatment for folks on the way to Mars and beyond.
Thank you, Michael, for this interesting lecture. I have here some questions from the auditorium. Just a second. Oops, here we go. You switched it off and my screen was off. Here's a question from Jonathan Hart. What efforts are being made to design such systems to be secure from the ground up? For example, prevention of spying of data or prevention of malicious activation of the systems.
Yeah, thanks, Jonathan, and happy to take any comments in person. We can take the written ones first, and then if it's easier, happy to discuss as well, and to hear others. I presume others are listening. But thanks, it's a great question, Jonathan. At least in terms of what we understand from ground up data security, and we have seen some integration of some other computer system research around protection of data buses, specifically around, as you know, certain aircraft and other communication systems have very similar telemetry systems. It's not human telemetry, i.e. compressed data around ECGs and EEGs, things that you would see in an ICU kind of data set, but they are very similar to how attack signals work and how you would try to circumnavigate or even prevent those from happening in, say, an aircraft, whether it be a military aircraft or a commercial aircraft. And those are the same, what we've seen in research has been the same application of ideas around protecting data buses against attack signals, only this time presumably in low Earth orbit and exploration class. The data bus is not for an aircraft, it's for a human.
Yes, and there was another question from Bridget Oppermann. But you answered the question actually, are there any systems in place at the moment to diminish the need for Wi-Fi and Bluetooth for further than low space orbit? And Atesh Gallagher mentioned from what he knows as a diabetic insulin pump user, there is very little security. His insulin pump could be connected to via Bluetooth and taught to deliver a lethal dose of insulin easily. And the focus is more on continuous monitoring, for example, pulse ox and smartwatch style monitoring or quick check medical equipment like a speedy doctor's visit or high-speed labs.
So I think that's two questions. I mean, the first one around low Earth orbit and Bluetooth.
Yes.
In terms of developments, look, we've seen you will be able to use Bluetooth in low Earth orbit, but I suppose that's linked to the second question around security. Again, we've seen not even going around low Earth orbit. We've seen here on in terrestrial settings here on Earth that there are issues around security when it comes to Bluetooth automated medical devices, and they don't even have to be automated medical devices. There are devices that you could transmit non-medical information, i.e. a remote control device that can very, very easily be the attack signal could be directed towards that a Bluetooth device very easily. This is not just a technological question, it's an ethical question, i.e. do you want to develop a device that can be easily hacked, and do you want to put someone's life on the line for it? And so the short answer to the question, I think it's a tremendously important question. We have colleagues at the University of Sydney who work on those issues. I'm not personally an expert. That said, I share your concern. It's really, really concerning when you're talking about automated medical delivery system for systems that could be hacked, whether that be in a terrestrial setting or in a space setting as well.
Are there any other questions from the auditorium? So then I would like to say thank you to Michael Wong for this interesting lecture, and thank you to everyone for joining the meeting. And I wish you a pleasant time at the Mars Society Convention. Goodbye, everyone.
Thanks, everyone, and please feel free to get in touch.
Thank you.